There are two very useful quantum operations that you should really know about, and in order to see the relevance of the Hadamard transform and the quantum Fourier transform, let me just go back to the very beginning of our lecture course when I was telling you that quantum information science or quantum computing is essentially about quantum interference. It's a huge multi-qubit quantum interference experiment. And we were looking then at this golden circuit where we had a qubit undergoing through the Hadamard, then the phase, and the Hadamard operations. So that was our single qubit quantum interference experiment. Now we want to generalize it now. We are going to look at many qubits, and we will be introducing phase factors using quantum function evaluation. So I want to now take this circuit that you understand quite well. You understand the role of the first Hadamard is just starting the quantum interference. It's generating those different computational paths, in this case just two computational paths. Then the phase gate is very important, right? Because it introduces those phases, and the whole quantum interference experiment really depends on the phase shifts here. And then of course we have to bring all those interfering paths together in order to see quantum interference, and that's the role of the second Hadamard gate. Now when we have many qubits, and it's a little bit of a spoiler, so we are going to be looking at the situation where we have many qubits here, and we will start quantum interference with something that we will now call the Hadamard transform. Then here we will introduce phase factor using quantum function evaluation. For this I will need another register. We'll talk about this in a moment. But look at the first register, because that's really what matters here. And then I want to close quantum interference. So I'm going to have another Hadamard, and then we can do bit by bit measurement. It doesn't have to be Hadamard. It really depends on what is this binary string. What is the meaning that you give to the binary string? So the opening sequence is usually Hadamard because we want to have equally weighted superposition of all possible binary strings, but the concluding sequence of gates could actually be something that we called a quantum Fourier transform. So for your convenience, here are the two operations that we are going to use in the context of quantum algorithm. The Hadamard transform, which is essentially applying the Hadamard gate to every single qubit in your register. You have n qubits and you apply the Hadamard to each of them. So that's your Hadamard transform. So why is it useful? Well, it opens quantum interference. So when you start with all qubits in state 0, you have equally weighted superposition of all possible binary strings that you can have. Now, of course, when you act on qubits and some of them are in state 0 and some of them are in state 1, then you have to be careful because some of the terms will have a minus sign. So just to account for this, there is this very simple formula here, which says that if you take x is a binary string from your computational basis, it represents just a sequence of zeros and 1, then what you will get at the output here is again equally weighted superposition, but some terms will have a minus sign, and in order to see which one, you will effectively look at this expression here. You have minus 1 raised to the power x dot y. So x dot y is this inner product of two binary vectors. Think about x as a binary vector. You have ones or zeros there, and the same for y. Then you just take a scalar product, so you multiply bit by bit and add modulo 1. So this term here, x dot y, will be either 0 or 1, and therefore the phase factor in front of this expression here will be either +1 or -1. So for example, here, if you can see that if you act on two qubits, so we have 4 possible binary strings that the two qubits can represent. So it's 0, 0, 0, 1, 1, 0, 1, 1. So when you look at this operation, you see that this is essentially a unitary operation that maps. So for example, if you start in state 0, 0, you can see that you have equally weighted superposition of 0, 0, 1, 1, 0, and 1, 1. But if you start in some other state, so for example, you just start in state 1, 0, then you can see that you will have equally weighted superposition, but in this case, terms 0, 0, 0, 1 will have a +1 factor, and 1, 0, and 1, 1 will have -1 factor. Now, if you, however, want to think about your binary strings not as binary strings, but as representing something, for example, representing numbers, so you take 2 qubits again, and you say, okay, 0, 0 is number 0, 0, 1 is number 1, but, you know, 1, 1, for example, can represent number 3, and 1, 0 can represent number 2. So you now are giving some meaning to your binary strings, and your underlying algebraic structure that you are going to operate is different. So in this case, for example, we are talking about the group Z2n, and here we are talking about group Zn. N is usually some power of 2. So we can construct something that is probably more familiar to you, the digital quantum Fourier transform, and again, in this case, we don't only operate as here with plus and -1, but the structure becomes richer because we have we can play with phase factors, which are complex numbers, and when we operate on 2 qubits, again, we can see that this will generate a unitary operation. You can generalize this construction. You can talk about some other groups, not necessarily groups of this type, and in which case you label your matrix element with elements from the group, and we can define quantum Fourier transform in terms of the so-called character of the group. But I'm not going to go into details. So for us, the most important is the Hadamard transform, which is a quantum Fourier transform on group Z2n, and a regular quantum Fourier transform, which is this expression here, which is constructed in a slightly different way, not really very different way. The circuit for quantum Fourier transform has Hadamard gates, but the Hadamard gates are interspaced with conditional phase shift gates. It can be efficiently implemented, and it's quite often used in algorithms where we think about our binary strings as integers. So then the quantum Fourier transform is used as the usually as the concluding part of the algorithm. It allows us to pick up some interesting patterns in phase factors, which will be encoded in the first register. But we will come into this.